Welcome. In this video, I'm going to take a look at the addition reactions of the alkenes. And this also comes from section 10.2 in the Brown SL chemistry book. So the general formula for an alkene is CnH2n because it's an alkane with one double bond. And when you form a double bond, that eliminates a bond site or a hydrogen from each carbon. So it makes sense that the general formula would be 2 less hydrogen than you see in an alkane. And if you extend that to an alkene, when you put the triple bond on, you'd remove 2 more hydrogen. So the general formula for an alkene would be Cn, or an alkyne, I'm sorry, would be CnH2n minus 2. Both alkenes and alkynes are unsaturated hydrocarbons because they have that multiple carbon-carbon double bond. We're going to talk about alkenes that have just one double bond, but it's possible for them to have 2, 3, or more double bonds, and then you call it a diene, a triene, etc., to indicate how many double bonds are in the structure. Regardless of how many double bonds there are, a double bond always consists of a sigma bond, which is the stronger bond because it has the middle position for its electrons, versus the pi bond, the second bond, which has to form around that sigma bond, much like a bun around the hot dog. So the pi bond is going to be more easily broken and highly reactive because its electrons are more exposed. So alkenes easily undergo addition reaction where the double bond opens, and it's just that pi bond that opens, so the carbon remains single bonded to each other, but there is one new bonding site available on each carbon, so each carbon gains a new atom or a new species bonded to it. And this means that your alkene is now going to be saturated in some kind of alkane. So the 4 really common addition reactions that I'm going to look at in this video are where you add a molecule of hydrogen, halogen, halogen halide, or water. So on this slide you can see that I've highlighted on these 4 different addition reactions. First of all, you see where the double bond is on my propene here. And I'm using propene, and it looks like ethene down lower. But in each case, the double bond, the pi bond opens up, so just the one bond. So the carbon-carbon remains intact. But now we have these 2 bonding sites available. And so if it's hydrogen being added, each carbon picks up a hydrogen. So it just becomes propane. But if it's a halogen, bromine, now each carbon picks up a bromine atom, and we call this a dihalogenoalkane because there's 2 halogens on my alkane. If it was a halogen halide, like HCl, then one carbon would gain the hydrogen and the other the chlorine, and this would just be a halogenoalkane. And now think about how much work it was to form the halogenoalkane from an alkane where you have to substitute the hydrogen versus this reaction, which takes place very readily without UV light, without that big reaction mechanism of initiation, propagation, and termination. So this is the far easier way to form halogenoalkanes. And then finally, with water, we end up with an alcohol because the OH group substitutes onto one carbon and the hydrogen on the other. Now you notice with the water mechanism here, they show an additional step that you need H2SO4 as a catalyst. It looks like it's a reactant here, but it's actually a catalyst to get it going because you form an intermediate product with the HSO4 minus attached to the carbon, and then the OH comes in and substitutes it. But again, all 4 of these reactions happen pretty readily at room temperature. So we'll take just a closer look at each one on the following slides. So hydrogenation, it's got the word hydrogen right in it, so don't confuse it with hydration, which is adding water, which we'll also look at. But hydrogenation is when you have an alkene with hydrogen, H2, and it's simply going to form an alkane. The conditions usually involve 150 degrees Celsius, so not real high, and nickel catalyst. And what do we use this for? Well, it's commonly used in the margarine industry. Margarine came around back, I don't know how long ago, well over 50 years ago. But it was the answer to butter because butter wasn't considered to be healthy for you because it's a solid at room temperature. That means when it gets into your arteries and veins, it tends to clog them up and be a solid in there too. So oils like olive oil and corn oil were considered much healthier, but who wants to pour oil on their bread? Back then that wasn't considered real appealing, and a lot of people still don't find that appealing today. So they came up with this idea of margarines where they convert these healthier unsaturated oils into the less healthy saturated fats called hydrogenated fats. And it just means more hydrogen. So they add hydrogen to these oils and make them slightly solid or soft solids at room temperature. This is also the process we use to produce trans fats. If you hear about trans fatty acids, these are even worse for us, and they've pretty much been eliminated from most products at this point. So the second reaction is when an alkene combines with a diatomic halogen molecule. And we call it a dihalogeno compound because there are two halogen atoms on the alkane. So this reaction happens quickly at room temperature. It'll cause the halogen to lose its characteristic color, like iodine and bromine tend to be kind of brown-orange, chlorine more of a green. So that color will disappear as the halogen becomes part of the dihalogeno molecule. But notice each halogen atom is on a different carbon. A really common mistake is for students to draw both halogen atoms on the same carbon, which can't happen with this mechanism because it's the double bond between two carbon atoms opening up, leaving a bonding site on two different carbon atoms. And again, the name is a dihalogenoalkane since there's two halogen atoms within one alkane molecule, which is slightly different than when you have a hydrogen halide like HCl combined with an alkene, because now one carbon gets the hydrogen and one carbon gets the chlorine, so you form a halogenoalkane. So this halogenoalkane is going to look and behave exactly like the halogenoalkanes formed when you substitute on an alkane. But in this case, the process happens very quickly at room temperature. It does not involve the multiple steps in homolytic fusion or initiation, propagation, and termination. It's a much simpler process for an alkene to pick up a halogen than it is for an alkane to pick up a halogen. Interesting thing though is HI is now the most reactive. When it's halogen, F2 is the most reactive and the most likely to form a halogenoalkene, and actually a dihalogenoalkane. But when it's a hydrogen halide, HI is now the most reactive because HI will form the weakest bond with hydrogen, whereas HF will form the strongest bond. So now your reactivity flips for the halogen family when they're already combined with hydrogen or a hydrogen halide. And then hydration, this is adding water. Hydration, you should be familiar with the word. Hydrate means water. So hydration, don't confuse it with hydrogenation where it's H2. So hydration, you have an H and an OH group. They're going to end up on two different carbons. And if you think about that, that means you're forming an alcohol. And I'm not quite sure why they showed the H and the OH on the ends of these carbons, but it would be exactly the same if they'd shown them down below like they did on the previous examples. Again, the one thing to note here is that there is actually two steps here. Even though this reaction happens quite easily, it does usually use sulfuric acid as a catalyst to form this intermediate step where HSO4 with a -1 charge bonds to the carbon, and then the OH comes in and replaces that. So again, to distinguish between alkanes and alkenes, the alkenes will react easily at room temperature with a halogen, whereas the alkanes will need UV light. So a halogen test without any UV light present is an easy way to know if it's an alkene or an alkane. If it reacts, if the color disappears from the halogen, it's an alkene and reacting. If the color persists, it's an alkane and no reaction is occurring. You can also burn it. Burning's a little harder. I mean, in the halogen test, it requires the observer to notice if there's a color change, but that's pretty easy to see if the color is getting lighter or disappearing. The soot test is a little more subjective, but if it burns sootier, you can assume it's an alkane versus an alkane. And then this also means the soot test would become even more magnified for an alkyne with a triple bond or a benzene ring with just a 1-to-1 ratio of carbon to hydrogen. So you will see more and more soot produced as that carbon to hydrogen ratio increases or hydrogen to carbon ratio decreases, whichever way you want to consider it.